the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics podcast. I am your host, Parker.
And I'm Ray, and we welcome you back to episode number 80.
Whoa.
The big 80, where today we have for you guys another History of Physics episode.
Officially our most popular type of episode that we put out on this channel.
Mm-hmm. So this particular episode, so I know for the last few History of Physics episodes, we've been very, let's just say, inconsistent with the people that we're talking about, because sometimes, you know, they have something directly to do with each other, like Einstein and Bohr, and sometimes they're just completely, literally, like Pythagoras and like Euler, like different times and everything.
Still interesting though.
The point I'm trying to make is that it is still very interesting, not to say it's not, but I think maybe we can try, especially with this particular episode. I mean, you've already read the title, but with this particular episode, these two individuals quite closely related. You know, like their fields are relatively similar, or at least one has used a lot of the other's work.
Do you remember
their field?
Sorry. Do you remember what the first episode was? Because first history episode. Well,
yes, like, Richard Feynman. I was Richard Feynman, and you were
Newton? Was it Newton?
Yes, I think you were Newton.
Okay.
I think you were Newton.
And the second one was the Fourier and Taylor.
Yeah, so I mean,
that one was.
They were just cool people that we were talking about. But maybe now we can get in. I mean, let us know in the comments below what you guys think of this. But maybe now we go into similar fields of people. So today, for those people that have not yet read the title and just downloaded the video because, you know, you love it already, we are going to be talking about James Clerk Maxwell and Ludwig Boltzmann.
From the same era in time.
Same era, same, like, similar fields, and you literally have heard both of their names together, Maxwell, Boltzmann, a lot of times.
And, so I have, you know, some kind of connection to Maxwell because I actually took electromagnetism last year, which Ray skipped out on.
Okay.
But you'll get to it. You'll get to it.
I'm taking it next semester.
Next semester.
Just, the number of courses were different. Anyways.
But yeah, at the very end, the very last unit of that course was actually on Maxwell's equations. Now, the thing is, Maxwell's equations are actually very complicated. But obviously, we looked at the physics behind, you know, electrostatics, magnetostatics, and then the connection between the two, and then presented Maxwell's equations. So I got like a brief introduction. I feel like I can explain them as best as I can, which I will do, obviously, when we talk about Maxwell. But yeah, maybe Rayhan will learn a little something as well.
I mean, I'm very excited to learn it next year anyways. I mean, maybe I can get a little sneak peek of what is going to be in my course. Sure. But so definitely, and Maxwell's equations, I mean, for anyone who is in higher level physics, or even if you're in lower level physics, probably heard of that term or of that phrase, Maxwell's equations. Super important for the fundamentals of electricity, right? And Boltzmann comes in and actually uses a lot of Maxwell's equations to do stuff with him. And I mean, we can obviously get into that, but like they do a lot of their stuff together because basically the fundamental math, a lot of it comes from Boltzmann. And again, we can explain like what the differences are between the guys and stuff like that and what fields they specialized in. And a lot of the physics came from Maxwell, especially with like some of the equations. So, I mean, I think it'll be fun to see, you know, what both of them did together and what they did separately and stuff like that.
100%. Yep. But before we actually get into the podcast, we have to hit you with a little bit of news.
A lot of news, because this week we are not the biggest week. I think next week will be a lot bigger, because this week we are sitting at 238,000 downloads.
Oh my. I think we're averaging over 1,000 downloads a day.
So Now, interestingly enough, we are actually recording this episode a few days earlier than we usually do because I'm a little unavailable this weekend. So by next Saturday, we're probably going to be there.
250,000?
We're probably going to be there.
Oh my.
Yeah.
All right.
Yeah.
I can see it.
So that's going to be very entertaining. That's going to be amazing. It's truly crazy milestone. So again, obviously, thank you to everyone who keeps downloading it. And talking to our Spotify followers out there. Again, all the other followers, you're not forgotten. It's just a lot harder to get the analytics for all the separate ones. Spotify is just a lot easier. So we just repeat that. So Spotify, we're almost at 15,000. We're at 14.8 roughly. So we're almost at 15,000 followers. So thank you to everyone.
That's cool.
Thank you to everyone who continues to follow us. And lastly, gotta get this in too nowadays, the YouTube subscriber count. So we hit 1,000. I think, did we hit it a month back? More than a month back?
More than a month.
More than a month?
Yeah,
Sorry, I think I'm
way
forgetting.
More than a month.
So we hit 1,000, but relatively recently, relative to when we started. Now we're at 1.8.
Let's go.
Yeah, we're at 1,830 subscribers, at least the day we're recording this. So hopefully, I mean, will we get 2,000 by next week, you think?
I don't think so.
I don't know. Probably not, but let's see.
But if you do right now go on YouTube
Yeah.
and hit the subscribe button,
Maybe
anything can happen.
Yeah, maybe we'll get
So-
closer to hitting that 2,000.
Boom. If you're watching this, listening to this, make sure to follow, subscribe, like, and leave a comment. Why would you leave a comment?
Why would you?
Because every single week we pick out a comment of the week.
No
Today's comment comes from, his name is Sergio Perez. He left a comment on last week's video, and it's a pretty long comment. I'm not going to read it all, but essentially he says that like math was hard for him because of like developmental alterations and ADHD and those types of things, but he actually finds it easy to listen to our podcast, and he can actually visualize the math and the physics that we talk about here on the audio format, because we do have to break it down because it's audio only, kind of video, kind of video, but mainly just audio. So we do have to break it down and all that. So yeah, he says, thank you for inspiring me to stop fearing math. He's now starting to read math books on his own, and he says hopefully next year he's going to enroll in physics. So thank you so much for your comment, and make sure to leave a comment if you want to be next week's comment of the week.
I think that's that. I think that's that.
Do you want to go first?
Why not? Let's begin with Ludwig Boltzmann. When was Maxwell born, by the way?
He was born in 1831.
Okay, so yours is a little earlier. So Ludwig Boltzmann was born in 1844, actually. It's a little different date there. And he was born in Vienna. Yeah, so he's an Austrian physicist that, he's basically an Austrian physicist. He wasn't really in a family of scientists or anything crazy like that. His father, I believe, was simply like a tax agent collector, something like that. So it wasn't like a rooted in science kind of families where it started, right? And it simply happened that a couple years later, he simply enrolled himself into mathematics and a mathematics and physics program at the University of Vienna, and just continued with that. And again, in this time, like the 1800s, Parker and I were talking about this just before the episode, people got into university relatively soon.
Yeah.
Like relatively soon. Now, I guess, there are some people that, started at 14 and 15 and stuff like that. And Boltzmann got his PhD by the age of 22, right? So he was a full doctorate level scientist at the age of 22. Now, in this whole endeavor of his, of studying at the University of Vienna, the director of the physics of the physics faculty was none other than Joseph Stefan. Now, Stefan, if maybe don't recognize that name, maybe the Stefan Boltzmann Law, may have heard of that. That might have got something for you. The Stefan Boltzmann constant, another big one. So again,
Isn't that the same thing,
yeah,
though?
no, well, no, I mean, no. Well, no, the Stefan Boltzmann law is a law. The Stefan Boltzmann
Yeah,
constant
but it's
is
in the law.
it's
so
a constant in the law.
yeah.
But I'm just saying that's probably where you've heard the name Stefan from. And anyway, so while Boltzmann was working, while he was in university, I'm assuming he simply got close to the director. So he got close to Stefan, and they began working together after. And actually, his very first job, or one of the big ones at another university in another country, he got because Stefan had sent in a letter of recommendation, and he had said, "Hey, he's definitely good." And the interesting thing about Boltzmann in his, or at least personal lifestyle, is that he was very erratic individual. He kept bouncing back and forth between jobs, like 1 or 3 years. He used to be like professor at certain universities, to the point where this is a little funny, to the point where I believe it was the Austrian emperor at the time that wouldn't give Boltzmann a job at the university that he was applying to because of how erratic because he was like, "You're just gonna leave again, what's the point? So I need a guarantee that you're gonna stay here," kind of thing. And that was, I just find that a little funny that he was so into it that he just kept going back and forth. Again, not too sure why. I'm just assuming maybe just wanted different experiences, but I mean, that's up to him. And in this whole trip, right, where where I guess he's doing a lot of things here and there, is also where he formulated a better relationship with Stefan. He formulated better relationships and was talking to a lot of the famous physicists at the time. I don't believe he ever directly spoke with Maxwell. I could be mistaken, but I think it was just their knowledge.
They were studying the same. Well, they weren't only studying one thing, right? But they were both studying at the same time the kinetic theory of noble gases.
Well, it started with ideal gases.
Ideal.
So all is ideal, right? That's how the math always starts, and then you simply generalize it. So it was the kinetic theory of gases was originated. I mean, there's so many people that actually thought about it.
Yeah.
It's just that Boltzmann actually put it on paper and succinctly stated what it is, what the relationship is. And then I believe Maxwell's, again, equations come into it because, again, they simply assist the proof. But again, I don't think there was ever any like, "Hey, Maxwell, how you doing?" kind of thing between the both of them. So that's a little bit of Boltzmann's history. I don't think I'm missing anything big. If I do, I'll maybe butt in, but I think that's basically it.
All right.
Let's listen
a little bit about
Maxwell.
Maxwell. So James Clerk Maxwell.
One thing, sorry, I just forgot.
Oh my.
Sorry. One thing I just wanted to mention that I found really sweet about Boltzmann. Very nice individual. Not that I do, but his wife, not at the time, but so at the time, women becoming, going into science, going into like professorship, not really heard of, like almost like not even allowed to the point. And there was this woman, Henriette, who was applying for the math and physics, and Boltzmann at the time, I'm assuming they may have started a relationship together of some sort, and he had appealed for her to get into the program, and she got in because of him.
Oh.
And then they ended up getting married right after. So I just found that really cool. A little more extra part in his life.
That's fun.
You can go. Let's hear a little bit about Maxwell.
So James Clerk Maxwell, he was born on a summer day of 1831 in Edinburgh in Scotland. He was a Scottish man, okay?
Nice.
So let's just say that his family was comfortable. Okay? When he was a young boy, okay, they moved on they built an estate, his family, his parents, on a 1,500-acre plot of land, okay? Oof. So he had space. Oof. He had room to explore, a little section of the earth to himself, okay? And fun fact, his dad's name, or his family name, is actually not Maxwell. It's his dad's name is John Clerk. he added Maxwell to the end of his name after he inherited a property that was from a Maxwell.
Oh,
So he inherited a property and he said, you know what?
how would he inherit from a Maxwell though? Like,
I don't know the details,
that's so weird.
but yeah, he literally inherited an estate, a Maxwell property, and he put the Maxwell on his name. So James Clerk Maxwell, the Maxwell equations, could have actually been called the Clerk equations, but you know,
Wow,
little
that
fun
would have
fact.
been very
there.
different.
Little
Very
fun
different.
fact.
Very
So-
different life there.
So James was actually, should I call him Maxwell or
I think you
James?
should call him Maxwell. I think James.
So, okay, Maxwell, when he was a kid, obviously, you know, he was good in school, but surprisingly, well, I don't know if this is surprising, but he was actually really good in English and poetry.
No, that is surprising. Why
And
would that not
he
be
could
surprising?
actually, he memorized the book of Psalm from the Bible. And you could like ask him, like, what is chapter this, verse this, and he could just recite it to you.
Oh,
Yeah, he did that.
that's pretty cool.
Yeah,
That's
no.
pretty cool. That's
when
pretty
when
cool.
he was a kid, like literally when he was like 10 or even younger than that. Actually, when he was younger than that, because his mom died in 1839, and it was his mom that was like supervising his church studies. So that's crazy. He had a crazy memory, I guess, and he was actually really good in school, but he never really like fit in. You know what I mean? Because it's kind of like an Einstein situation, but not really, because he would still get good grades, but he was just very smart to the point where like he needed, you know, he actually had a tutor, and the tutor was garbage, so they got rid of the tutor. And when he was actually 16 years old, well, he went to like this private school when he was younger than that, and he got a bunch of prizes for English, poetry, and he actually started when he was 14. He wrote his first paper. He was still in like when you're 14, you know.
He was 14 when he wrote his
No,
first
yeah,
paper.
He wrote a paper
Wow.
on mathematical curves and ellipses, curves with two foci.
Who even thinks of this at 14?
You know, he was drawing curves and writing papers at the age of 14, and this actual paper he couldn't publish himself because people thought he was literally too young.
Of course.
So he got his tutor, not the garbage one, a good one. He got a tutor to actually present it to the Royal Society of Edinburgh, and you know, it got picked up after that. He couldn't just go and do it himself, but he was 14. And he actually went to university at the age of 16. And guess what? He was taking, at the time, all the scientists were into like psychology, natural philosophy, as well as mathematics and physics. So he was taking those courses. And it was actually very easy for him. His course load was said to be light, and he had a lot of free time to study on his own. Okay? And so by the time he was 18, he actually contributed to 2 more papers. 18 years old. Think about that. Okay? And he was actually interested, or getting interested, while he was at the University of Edinburgh. By the way, I didn't mention that, but that's the university he went to. He actually had the opportunity to go to Cambridge after his first year, but he denied that opportunity and decided to stay and finish his studies at the University of Edinburgh. So while he was studying there, not his main focus, but one of his interests was the properties of polarized light, which is actually one of the keys to get into the door of quantum mechanics. But at the time, it wasn't even.
Yeah. Remember, quantum
around.
mechanics was a thing like early 1900s.
No, I know.
Not even middle.
I know.
I'm not saying against you. I'm just saying in general. Like what? Early, middle, mid 1900s, right?
Early 1900s.
Early-ish 1900s.
Planck was late 1800s.
Yeah, valid.
So depends on what you call the start. But yeah,
Valid. No, yeah.
like black body radiation is pretty much the start. So, anyways, the point is that he was interested in like topics that would unlock quantum mechanics, but it wasn't even there. You know what I mean? It wasn't even possible to start thinking about those topics, but he was still in that medium, I guess.
Mm-hmm.
Do you want to continue about Boltzmann?
I mean, not anything personal. If there's anything you want to continue about a personal,
not personal.
Okay, so then we can maybe get into a little bit about what these two individuals did. Now, I'm going to be completely honest, 100% sure about the chronology, because I know it kind of just goes back and forth with a lot of the different things, because I know, especially with Boltzmann, there's a lot of things that he did relating to the kinetic theory of gases with other people and with himself. So I'm just not entirely sure about the timeline, but I can just tell you guys everything that happened and everything cool about it. So maybe, I don't know about when you're going to talk about Maxwell's distribution and stuff, so maybe I wait a little bit, but we can start with like something, because you mentioned black bodies, so I just thought of that. We can start with the simple Stefan Boltzmann's law. Right, so that's actually one of a very famous laws that he helped derive using thermodynamic properties. So Stefan's law, which is how it originated, was a very basic equation, and then Boltzmann came into it, and I think he basically further proved the relationship between. So wait, what is Stefan Boltzmann's law? I should probably say something like that. It is the relationship between the temperature and, how do I say this simply? It's basically the energy given off. So the energy given off by any body related to its temperature, right? And that's basically the relationship. And the point that the original law was making is that this relationship is T to the 4. That means as temperature increases, your energy that your body is basically emitting is increasing to the 4th power.
And how is this? I feel like this is directly related to Wien's displacement law.
Yeah.
But Wien's displacement law is the peak wavelength, right? And then the wavelength is directly related to the energy.
Yes,
is
exactly.
That right? Okay.
So Wien's displacement law is also got from a. Yes, so that is basically to get your peak wavelength, to get your energy spectrum. And so, I mean, Wien's and Stefan Boltzmann's do agree with each other, which is actually a big proof that, I mean, obviously does have to happen. And again, it's just that relationship between like that energy that it releases basically and the temperature inherently of the body. So why is this even important? So you were mentioning black bodies, right? So this starts a little bit by talking about, well, what's a black body? So I think we have mentioned this before, but maybe a quick little recap. A black body is simply a body that absorbs all amounts of radiation equally. Now, in real life, nothing is really a true black body because nothing really absorbs everything equally or equal in intensity in every location on its body. So nothing is a perfect black body. But again, in physics, we always have theories that are with the ideal situation, and then we try to, generalize them down to what the real world is. So the idea of this radiation, it's actually called black body radiation, states that every body that has a temperature above absolute zero will emit some sort of radiation. And the simplest example of seeing what this energy relationship even is on a simple stove. When you heat up your stove, how it glows red. I mean, there's not actually any red coloring that's there. It's simply the metal from your stove that's so hot. The temperature is so hot that it is radiating energy that you can now see. Energy at which the frequency, the energy, again, when I'm saying energy, I basically mean light. Again, that's the energy that I'm talking about. And it's emitting it at a frequency that now I can see. Because right now, everything around us, you can't see any of it, right? You may have heard like the classic that all of us, we glow in infrared. So if you have an infrared camera, you can see everybody even in the dark. But if we're not giving off visible light, you can't see us. Unless you heat us up.
Well, think about this. If you had infrared eyes, just like we have visible light eyes.
Yeah.
So when you heat up a stove, like a stovetop coil, you see it become red because its energy the temperature gets to a point where the energy that it's radiating can be captivated by your eyes. But if you had infrared eyes, then even if you turn all the lights off, right, Ray's body to my eyes would be like a stove literally glowing, and I would be able to see him whether, it's dark or not. Because to us, dark is just the absence of visible light.
A visible light, exactly.
But light extends beyond the visible spectrum. And so if my eyes were infrared, Ray would just be like a walking, glowing body.
So a big thing about this whole experiment is also, and that's where the peak wavelength thing comes in from, so every body has this peak wavelength, right? So every body emits this radiation at a specific distribution of wavelengths, right? It emits it at, I'm trying to picture it and think about it, but it's simply it's if you want to think about it, it's just a right skewed graph. It's a right skewed Gaussian, and that's basically your standard distribution of your intensities or of your energies, right? So usually your most probabilistic wavelength is what they call your peak wavelength. So the distribution where it's most heavily centered around, right? Like the peak of the distribution will again be your peak wavelength. Now every body has a peak wavelength. So do we. And ours happens to fall in infrared. And the thing we were also talking about with Wien's displacement law is another relationship between wavelength, just to understand the wavelength relationship here. It's just a different formula that does the same thing. But at the end of the day, what it's really understanding is the relationship between a body's temperature and the radiation that it is actively emitting, right? And that's something cool that Boltzmann kind of assisted with and obviously helped prove, which is where he capped it off with Stefan.
And also, we're not just like speaking words right now. You can actually take, the average body temperature, plug it into this formula, and literally see that the wavelength that your body emits is in infrared. And, I was going to say if you heat yourself up to a certain... don't do that.
Don't do that. But, I don't think skin glows at any temperature at which we just won't just die. I think skin would probably require... Okay, let's not talk about this because this is all biology too, because I don't know what... Probably just burn up, right?
I don't know. But coming back to Maxwell really quickly.
Let's come back to Maxwell.
By the time he was 29, he actually went to 4 universities, whether it was to study or to teach.
Jeez.
29 years old, okay? So after he graduated from the University of Edinburgh and he went to the University of Cambridge. This was in 1850, so he was 19 years old, okay? Cambridge for his second round, and this time it was a mathematical round. So he went in. This was a 6-year period that he stayed at Cambridge. By the end of it, he came out with a degree in mathematics, and he also joined a secret society. So that's interesting. Where
like a secret mathematics society, or like a...
it was called the Cambridge Apostles. And it's like there's a Trinity College. At U of T, we also have a Trinity College, but I'm pretty sure it's inspired from Cambridge.
It is.
Cambridge's Trinity.
Yeah.
And he actually was a part of that. He was part of Trinity at Cambridge, and he was actually elected to the elite secret society.
Oh my!
Known as the Cambridge Apostles. And
wow, that's
that's where he learned within that elite society, he learned a lot about Christian faith and science in general because the elite would study science.
Wow.
Now,
very interesting.
He actually graduated second of his class behind another student, okay?
Is he famous now?
I don't think so.
No.
When I read the name, it did not ring a bell.
Tough.
But it was actually later announced that they were tied.
Oh,
they were tied.
That's funny.
Yeah. So technically he graduated first of his class. Congratulations to him. Yeah, that's that's pretty much it. He also, he published more papers. And while he was at Cambridge, he actually published his first paper on electricity and magnetism, not yet electromagnetism because they weren't unified yet. So it was electricity and magnetism. Now, after Cambridge in 1856, he went to the Marischal College, whatever. Here's what happened at Marischal College. That was interesting, noteworthy to say on the podcast. At the time, it was unknown how Saturn actually had rings because it was a huge stability issue, right? If Saturn's rings were actually like solid objects, it's completely unknown to like why they would just stay there.
Yeah.
And also if Saturn's rings were like not I don't want to say clumps, but like big pieces, big chunks, like made up of big chunks, then what would happen is that they would actually create clumps and be completely destabilized, and they would not be able to just sit there in space. And so it was actually it was chosen, that topic, the stability of Saturn's rings, was chosen as the 1857 Adams Prize, where if you solve it, you get a prize. And so
I'm assuming
Maxwell won it.
Okay.
And his solution was that the rings were made of numerous small particles, very, very, very small particles. And we actually saw this last year in our astrophysics class, where we were talking about Saturn's rings, and our professor, she said, if you take the ratio between the thickness and the like diameter, I guess, like across, like I'm not all the way across the rings. I mean like the thickness of the rings, like it's a ring, the thickness versus diameter, thickness.
Like a disc.
I say thickness twice. This doesn't make sense.
Yeah,
I mean, okay. From the outer radius to the inner radius, that distance.
Yeah.
And the ratio between the thickness of it is less than the edge of a razor blade. Okay? So if you take the width, the thickness divided by the width, it would be less than
a
literal razor blade.
Basically saying that it's really thin compared to the size of Saturn. Like that's
very, very thin.
Yeah, very. Or
no, I mean the Saturn's rings.
Saturn's rings are very thin relative to anything really. Just
anything
because they're so big.
Yeah.
Like the space that they're actually taking up is so gigantic.
Yeah.
Right?
And so guess how much he won for that back in
1800?
1857. How much did he win for solving that?
100 grand.
That problem? 100,000?
Is that too much? I thought that would be because it's $1 million right now for some prizes.
No. He won $130 or pounds. Pounds.
What? That's pounds. Appalling.
Well, if you think about it, like
even 130 pounds though.
No, but if you think about like inflation, like from the 1800s.
Probably. Right.
No, that's probably insane.
Right. You're probably right.
Probably very insane. Like a hamburger in 1950 was 10 cents. You know what I mean?
What? Oh,
I swear.
I thought you said 1850.
No, 1950 was like 10 cents.
No, I thought you were gonna say 1850, 10 cents.
No, imagine how much 130 pounds was worth in 1950. Now go back 100 years.
Thousand, probably no.
Now go back 100 years.
Valid.
That's all I'm saying.
He was probably a little bit rich. I mean, he owned 1,000 acres.
No, yeah,
of
he
land.
didn't need.
I don't think
his dad did, but he didn't need it.
I don't think he really needed anything.
He really didn't.
It was just nice that he got it.
So that's fun. Next, he went to King's College.
Oh.
This is in London, okay, and he went there actually to teach. He was actually appointed. I think the dean is that right? One sec.
Was it like the head?
Yeah, he was the head of
the physics department.
I think so.
Or the math department.
I'll let you know if I see
Wait,
it in the notes.
Was it math or physics here?
This is physics.
This is physics.
Yeah,
right?
100%. And this is where, in King's College, this is the notable part of his life, where I think this is like 3 years into his time at King's College, he published his famous Maxwell's Equations. So
Here it is.
And
Here it is.
at King's College, he actually had a relationship, like professional relationship, with Michael Faraday, which Michael Faraday was actually 40 years older than he was. But so, there's kind of a seniority dynamic there. But he was actually, he had a relationship with him where they would talk about, because Faraday's law, you know what I mean?
You have to do a Faraday episode.
You know what I
oh
mean?
my God, I forgot about Faraday.
So, yeah, and one thing about Maxwell, if you don't know Maxwell's equations, is that Faraday's law is actually one of Maxwell's equations, but it wasn't actually completely right. Maxwell had to add a correcting term. And then after he added that correcting term, it was now part of Maxwell's equations.
Snake.
Yeah. So before I actually talk about Maxwell's equations, we have to go back to Boltzmann to catch up a little bit.
Yeah, so let's catch up on Boltzmann's life a little bit more. So we've touched on the Stefan Boltzmann's law, and how cool that is. And he's done a lot of other things. Maybe we can now start with one of the most fundamental things that he did, which was the invention of Boltzmann statistics, or basically modern day statistical mechanics. So ways of physics, there are many ways to do physics, right? There's Newtonian mechanics, there's Hamiltonian mechanics, there's Lagrangian mechanics, there's Einsteinian mechanics that all basically work together. And that's the whole purpose of it, right? They have to make sense. Now there's another one known as statistical mechanics. And this is basically, and so while all of them have their own respective properties of how they work, how you can solve their equations of motion, stuff like that, statistical mechanics is based off of probability laws. And it's based off of finding processes in physics that can be dumbed down to simple probabilities. And it's really cool because Parker and I were actually doing a course last semester on thermodynamics. And statistical mechanics is basically thermodynamics.
It is.
It basically is thermodynamics. Yeah. So what is Boltzmann statistics like, or at least the idea behind it? A simple way to think about it can be that, and remember, this is where the probability theory, the quantum mechanics, none of that exists. So he basically simply says, hey, when a system reaches thermal equilibrium, right, there is something in this system which goes to an absolute maximum, and there's something that goes to a minimum. And when it's not in thermal equilibrium, well, that's not true. And obviously after, relationships and laws, again, a lot of theory, he, again, not sure if he was the first one to derive it, but I do know that he was the first one to kind of prove the relationship basically between entropy and its following microstates. So in the entropy episode that we had, we kind of explained this equation in crazy depth. So I'm not going to get into it right now. But basically the understanding of the entropy equation, and this was, again, formulated officially by Boltzmann, was, again, the constant in the middle is actually Boltzmann's constant. So also seeing how it can become very important. So again, fundamental understanding of this equation is that, well, we have a system that has many separated, okay, I don't want to use the word microstate because we haven't defined any of that yet, but like it has a very separate processes that can happen, right? Very many particles moving about. When this whole system comes to equilibrium, the number of random events that can happen basically go to a maximum. And this was a very foundational understanding of one of like the principles of understanding statistical mechanics with equilibrium conditions. So when a system reaches thermal equilibrium, the amount of random fluctuations reach a maximum, or the entropy reaches a maximum. So what that basically means is in all of statistics, everything can be explained very simply. Luck, for example, what we call luck, is basic statistics. You can see that when we tend to a large number of data values, all distributions, most of them at least, in the realm that we're talking about, move towards a normal distribution, every single one. And this is a very famous statistical fact known as the central limit theorem. As the number of measurements get larger, all distributions approach, not again all, some they do require certain properties. I'm not going to get into that, but they approach a normal distribution. And so is your life. Your whole life is dictated by a normal distribution. So if you're having a good day today, statistically, you're probably not going to have one tomorrow. Statistically,
Is that true?
that is actually true. So when you're having like really good poker hands, stuff like when you're even
Oh,
in
you're
cards.
talking. I thought you meant like emotionally.
No,
like you're
even
having a
no,
good
no,
day.
not emotionally.
I
No,
was like, what?
no, not emotionally. I'm just saying, when your luck is just good,
Yeah.
things just happen for you. Like that's not, a foreign entity. That's just statistics. That's because your life revolves around a normal distribution. On average, you will do certain things most of the time. So on average, you'll probably get a hot dog. But then I'm just trying to give an example. But then on the one occasion, on the tails of the graph, if you can imagine a normal graph, on the tails is where you'll get your very lucky, very unlucky. Maybe I grab sushi today. Maybe I don't eat today. Stuff like that, So those are like your two tail ends. And that's basically an idea that this whole distribution and applying these statistical facts to physics comes up with. That, hey, we can now reduce physics to simply these probabilities. So how probabilistic is something happening? And it started off with simply, well, again, this is where Maxwell comes into it as well. With the Maxwell-Boltzmann distribution. And this is a very famous, the Maxwell-Boltzmann equation, where he basically derives a formula for the, it's actually the velocity, right? Because there are multiple formulas that they do happen to derive together. Because of this particular relationship, it derives a lot of more relationships between properties of particles. But again, basically, the relationship that he came up with was what will be the average or the most probable velocity of any system of particles given certain properties. So given a certain temperature, given a certain energy, what would be the velocity? What will be the probability of something happening, right? Now, when I say velocity, again, I'm kind of making a lot of terms just a little bit easier to understand, because the actual thing or the actual equation itself is you're trying to find the probability of a certain microstate. So you're trying to find, well, what's the probability that this particle or this particular state is traveling at this velocity? And you can get that from the distribution. And all of this is grounded in Boltzmann statistics. Right? So basically a method of statistical analysis that he came up with to talk about with respect to physics. And it's really cool because one thing I want to talk, because I know your Maxwell's equation will go on long and super interesting too. That's why I want to talk about one other thing before we get in there. The Boltzmann Brain. This is really cool, man. This is really, I read about this today. I just started reading about it, and it's basically really interesting. So you know how the universe started, right? The idea is that there was thermal equilibrium in this singularity, and it caused by random fluctuations, the universe is now where it is. That's basically the best theory that we can come up with. Random fluctuations that follow statistical distributions. So again, this idea of statistical mechanics applying to even the universe, you can think, when the universe comes into a state of thermal equilibrium, the entropy will be at a maximum. Now, if the entropy is at a maximum, as I was mentioning before, the amount of random things that can happen also become a maximum. Random fluctuations, random events also tends to a maximum as entropy increases. And the interesting thing about this, now this is where the Boltzmann brain comes from. It's a very interesting fact, or it's basically a thought. It's a thought experiment about a brain being created in a void simply because of random particles coming together.
What?
And the idea was that it is more statistically possible for a whole brain to come together at a random moment in time, if we have infinite time, if we at a random moment in time, for all these particles to come together and form a brain with false memories and everything, than it is for the universe to exist right now.
How do you mathematically calculate
So again,
that?
we're not getting into that.
Yeah.
But that was a thought from the Boltzmann brain, and another extension of that thought as well. What about a whole Boltzmann body, right? Like a whole Boltzmann person, basically, connected, versus the probability that the universe just randomly came into existence.
So,
right?
Wait, what if? Okay,
Cool.
This kind of brings into question the fact that, like, okay, let's say you are a Boltzmann brain with fake memories. And right now, this is actually funny because this connects to one of the very first clips that we put out, which was like the idea that you're already dead.
Oh.
But think about this. Imagine if you are a Boltzmann brain that has been like loaded into the universe with false memories. And right now you're just accessing those false memories. You know what I mean?
I mean, no, that's actually,
you know what I mean?
That's actually a valid thought of this particular
Yeah,
experiment,
exactly.
because the whole point of this experiment is, well, how did science really evolve, right? Like we're like, what is the way? And again, this is basically through a use of philosophy that he deducted that this is a more statistically possible event. And it's interesting to see that, you know, something like this can even be thought of.
But also in this case, you kind of have to remove yourself from the human like side of things and think about how, okay, right now we think of a brain as a human brain. But in this universe, like a separate universe, because when you think about a Boltzmann brain that has false memories loaded into it, that means that everything that you know for sure right now is just a created false memory, which means the universe that you're living in is just a false universe. So then think about, what is the real universe in which the Boltzmann brain has been loaded into, and what are the rules of that universe? Would they be the same as this universe because you are a Boltzmann brain? Because the Boltzmann brain was thought about in the universe that we're in now. So I don't know. Think about that for a sec.
No, I mean, the whole purpose of this experiment was to think about it for a sec. Right. So it's definitely an interesting thing just to think about. Because again, we know enough about Maxwell and Boltzmann to just have a conversation. This is something I had never even imagined to even read about, you know, something like this. But it's super cool, you know, that someone, because even though especially at this time, all major physicists, all major scientists were in some way philosophers. Yeah. And this whole argument of the Boltzmann brain stems from philosophy. It's actually from a reductio argument that he gets that, okay, this is must be possible, and therefore we have Boltzmann brains. And he gets to this whole crazy logic. But it's basically just through simple philosophy and understanding that he kind of comes to this final statement, which I just find a little funny.
You know, we should actually bring back a philosophy episode.
No, we need to bring back a philosophy episode.
Because like, if we just talk about philosophy for a dedicated like whole episode, we could definitely think of some crazy stuff, which is always 100%. Fun, you know.
So anyways, I mean, that's basically Boltzmann's statistics for you.
Yeah.
Just a little bit of what he got into and contributed to science.
So
let's hear it.
In terms of Maxwell, here's what I was thinking personally. I don't think I'm going to get into the equations that much.
Get into it to the point where,
because there are other things I want to talk about too.
Well, yeah, so we can get into everything.
So I think maybe I'll start with the other things and then talk about Maxwell's equations. Okay, so first thing I want to say is that while Maxwell was at King's College, he actually calculated the speed of propagation of an electromagnetic field, because it is a field after all. If you have a charge, you know, let's say you spawn a charge. Back then, one of the questions was, okay, well, do the effects of this charge immediately are felt by other charges around, or does it take time for the electric field to actually propagate through space? And this actually has to do with the speed of causality. which, let me get to the point. The point is that he calculated it to be approximately the speed of light. Now, all of a sudden, you have, at the time, these unrelated things that are coming together. You have electricity, which is one thing. You have magnetism, which were two separate things. There wasn't a reason for them to be together at the time.
At the time, yes,
At the
for sure,
time.
of course.
And now you have...
I mean, there were still similarities.
No,
between
there was
them,
similarities.
You know,
but
still
there were a lot of
similarities.
differences as well.
Yeah, but like you can like just the simplest thing you can think about similarity wise is, hey, two north sides repel, two electrons repel. Oh,
And one thing that when you start to study electromagnetism is that you find that like metaphorically and literally and figuratively, electricity is perpendicular to magnetism. You know, in the sense where when we talk about photons, the electric field and the magnetic field are waving perpendicular to each other. But let's say you have like a line current. The electric field in that current is actually perpendicular at all times to the magnetic field, which actually rotates around the line. Okay? And so it's examples like this that have to, like, it makes you think of like, it's like they're perpendicular, but in more than just being 90 degrees to each other. And there are a lot of, I feel like I'm not speaking into the mic properly, but anyways, okay. So now you have these electromagnetic fields that are somehow related to the speed of light. Why does the speed of light, like, why did it come into play? So now we know that photons, light particles, are actually intertwined with the electromagnetic force, right? They're the force-carrying particles. So obviously to us, we're like, okay, it propagates at the speed of light because the what is it called? Lepton? No.
what are you talking about?
Force-carrying particles.
What?
No, like a force-carrying particle is called
Bosons.
Bosons. So, really?
Yeah, lepton is a type of so electron is a type of lepton. So leptons and fermions are the particles.
I never remember this.
Bosons are the force carrying particles.
So bosons, it's like the photon, which is the force carrying particle of the electromagnetic force. Of course, obviously, then the electromagnetic field would propagate at the speed of light, but at this time it was a discovery.
It was a crazy.
It was a crazy discovery. And actually, one thing that I thought of at the very beginning of the podcast, but I waited till now to say, is that Maxwell's equations at the time were equivalent in terms of innovation and not physical advancement, but advancement in the field of physics as Newton's equations of motion. F equals ma. Part 2 is Maxwell's equations. And then part 3 is the field equations, general relativity / also quantum mechanics. Like the staple equations in history, Maxwell's equations were, the successors of Newton's equations. Okay. Let's just talk about Maxwell's equations.
Let's just dive a little deep into them because I wanna,
Okay.
Let's hear it.
So let's see how far we get. But let's talk about the very first Maxwell equation.
Okay, let's hear it.
So if you were to see this, it would look something along the lines of.
Don't say.
No. I'll just listen. It's the divergence of the electric field is equal to the charge density divided by epsilon naught. That is the first equation, and if you study electromagnetism, you'd also recognize this to be the differential form of Gauss's law. So Gauss's law, we usually see it in the integral form as the surface integral of the electric field is equal to the enclosed charge divided by epsilon naught. Well, a little bit of calculus and common sense can bring us to the differential form. It's actually not that hard, because using the divergence theorem, the surface integral of a vector field is equal to the volume integral of the divergence, right? And if you think of the enclosed charge of a Gaussian surface, well, charge density is charge per unit volume. So if you just integrate the volume enclosed by that surface, you take the volume integral of the charge density, then you get that enclosed charge. Now, all of a sudden, on both sides of the equations, you have a volume integral over the same volume. So obviously, if you have a volume integral over the same volume, and they're equal to each other, then the integrands have to be equal. So now on one side, you have the divergence of the electric field, and on the other side, you have the charge density. So boom, there you go. You have the differential form. And it looks like nabla.e. Anyways, I love talking about the equations. Okay, so that is the very first
interesting
Maxwell
relationship that he definitely got there between all of these, because also try to explain the actual equation a little bit, like the significance of the relationship,
Well, I mean, that's a little bit hard. I would have to get into like the literal physics of, Gauss's law.
valid.
Which,
but just, I don't know, brief, because like, I don't know, if you just state the equation, I don't know what they're like, what is someone gonna do with that? Like,
I mean, it's interesting.
put a little bit of context.
Here's what it says.
Why is this equation important?
Well, here's what it says. Essentially, the divergence is a measure of going away. You know what I mean?
I mean,
like if you have a surface in 3 dimensions, let's say it's just a sphere, and the divergence of a field is positive, it means the field tends to move out of the surface.
Valid.
And so if you think of a charge and you draw a sphere around that charge, the electric field, the tendency to go out of that sphere is exactly equal to the charge density.
It's
and
basically
the charge density being just a delta function
Mm-hmm.
at wherever the charge is, right? Because everywhere else there's no charge, and then at one point you have that charge.
So
and if you know delta functions, when you integrate overall space, you're just gonna get whatever the coefficient is next to the delta function. And if your charge has a charge of q, then how do you describe the charge density? Well, it's just q times the delta function, wherever the position is. When you integrate overall space, you get q as your charge enclosed in all space. And if you just have a sphere centered at that charge, when you do the volume integral, then boom, your charge enclosed is whatever the charge is. But obviously you don't have to deal with point charges. You can also deal with continuous distributions, like a sphere of charge, where in that case you'd actually have to see the spatial dependence of the charge distribution and actually do your integral. And let's say you're lucky and you have an idealized problem where the charge density is dependent on the distance from the middle, then it's an easy spherical coordinate integral. Boom, you're done. Mm-hmm. Okay. Is that enough about Gauss's law?
I think that was a relatively better explanation for sure.
Okay.
100%, 100%.
So, I forget what it's called. Coulomb's law. Okay. There's a general form of Coulomb's law that you learn in university, and it's described as an integral. Usually, let's say in first year of high school, you learn Coulomb's law, and it has to do with point charges. It's equal to Q over R squared, and that's the electric field or the force or whatever. Is it the force?
What? Yes.
Okay.
Yes. It's the force of the electrostatic force.
But Coulomb's law, if you divide by the charge of the test charge or whatever, you get a value for the electric field. Well, it turns out that you can
F over Q is the electric field.
Yeah. You can actually generalize Coulomb's law to deal with distributions of charge, which obviously is much more useful and harder to do. So that's why you do it later on. But it's actually an integral over the charge distribution. Now there's another law in magnetostatics called the Biot-Savart law. And it's analogous to Coulomb's law, except now it's a vector because magnetostatics has to do with vectors.
So instead of the point charges, they're each vectors now, basically.
No, not necessarily.
Because I've not seen this equation.
Okay, so what you do is in electrostatics, it's a dot product, which is why you get God, there's so many memories coming back to me as I'm stating
there's also
these.
a lot of foundational stuff that we probably mentioned in like episodes here and there, but it's just like, sometimes it is a little bit, I mean, it's very reminiscent, especially when we get into some of these topics, and we just start remembering, hey, in first year we had all these discussions, but yeah, I think most of it is simply just remembering the information that we learned so long ago.
Yeah. So the electric field evaluated at some point has to do with your charge distribution and where your charges are in space. And so what you're actually doing is you're integrating over a volume where the charges are. And inside the integral, it's going to depend on the distance, each, dq, each small contribution to the total, where that distance is to the point you're evaluating at. And so you're evaluating the integral over this r prime coordinate, which is r prime is the position of each little contribution, and the distance from those r primes to the actual r, which is the position that you're evaluating it at. Okay, when we get to magnetostatics, things change a little bit. Because
and this is still under Maxwell, right? Magnetostatics is Maxwell, is that correct?
Well, Maxwell is like everything.
Okay.
But the reason why you start with magnetostatics is because it's easy. So
sounds
there
fair.
you go.
Sounds fair.
So I'm looking for my notes on the Biot-Savart law here. But okay, from what I remember, it's a cross product this time, because magnetostatics have everything to do with the right-hand rule.
That too.
So current, you point your thumb in the direction of current.
I think I've seen this equation.
And then using the curl of your fingers, you can then tell where the magnetic field is. So if you have just a line, then boom, you use your right hand, your thumb is in the direction of the line. And now you know that the magnetic field is curling rightwardly around whatever that means.
Rightwardly.
It's curling around.
Rightward. Okay, yeah, but it's curling around wherever.
Around the
I mean, again, rightward is for those viewers. Again, if you're just listening to us, then you probably didn't see Parker's hand go that way.
Yep.
But yeah, I mean, basically it just depends on wherever your fingers are curling towards. Because, I mean, the fundamental behind this whole rule is simply because your thumb and your fingers point in perpendicular directions, right? And everything that stems out from the right-hand rule, which is always related to vectors, simply comes from the fact that there are, in fact, perpendicular relationships. And this whole thing starts from electricity and magnetism being perpendicular relationships, right? So we kind of get that relationship there too.
So the Biot-Savart law, it's a cross product between the current and the position.
So is this one of Maxwell's equations?
No, but it's related to, because this is how you calculate the electric field at a certain point.
Cool.
Now you have to integrate over your charge. It could be a line. It could be like a wire is like a three-dimensional.
Whatever your surface. Basically,
current.
it can be a surface.
It could be a surface, but the most general form is a volume integral of your current. And it's pretty complicated. But here we go with the second Maxwell equation. It states that the divergence of the magnetic field is equal to 0. Oh. Which you can actually show because you have an equation for a general magnetic field. If you just take the divergence of it, then you'll see that it's just always equal to 0. There is actually no name for this equation. It doesn't come from anywhere. It just comes from literally taking the divergence of the magnetic field and boom, you get 0.
Let's get the importance of that though, let's get the importance of that. The divergence of the magnetic field is 0. That means on average, or not on average, but it is simply not so the vector field is not pointing what? So it's always like what is the one line summary of this equation? Would it be like, my understanding would be like the magnetic field is always enclosed almost?
Yeah, something
Would
like
that
that.
would that kind of be a one-liner thing?
Yeah.
Because it's always enclosed in whatever volume or whatever surface that you're doing it in, because it's not going out or nothing is coming in, right? Because coming in would be a negative divergence, going out would be a positive, but this is just 0. So that, I'm assuming, simply says that. That's pretty cool.
Yeah. And now, here's the equivalent to Gauss's law, but in magnetic form. Okay, it's ampere. Well,
Ampere.
It's a French name. Ampere.
Oh,
that's how you say it.
Oh, I
Anyways.
just say ampere.
But so
Parker with the
instead of it
French.
being a surface integral, it's actually a line integral this time.
Ooh.
And so you take a line integral, and the easiest case would be to just take you take a line current, and then what you do is you take a loop. Instead of it being a Gaussian surface, it's an Amperian loop that you integrate over.
Oh my!
And
Cool.
so
I like the name.
the line integral of the magnetic field dotted with dl, right, whatever your line is equal to mu naught, which is the magnetic version of epsilon naught, and times the enclosed current. And so you can kind of think of the Amperian loop. It has to be a closed loop, by the way, and this loop has a surface that it encloses.
Yeah.
And whenever you integrate over the B field, you will get the total amount of current that is crossing that threshold. Okay? And so if you have two opposing currents, it'll come out to 0. But the best part about this is that it doesn't matter how it's distributed. No matter what, if you know the B field, you will get the total enclosed current that passes through that loop.
B field, by the way, is the magnetic field. Just letting you know.
Yeah.
Also, I did a quick search, and the second law is actually just Gauss's law for magnetism.
Okay.
It's just, while the first one's just Gauss's law, the second one's just Gauss's law for magnetism, because it just applies for magnetism.
So Ampere's law, the same way that you have an integral form of Gauss's law that turns into differential form, the same thing applies, except this time you use the curl theorem, and the curl theorem has to do with the curl and line integrals. So you turn the line integral of the B field into a surface integral of the curl. And then on the other side, of course, you know how I was talking about current going through a surface? Well, you can just turn the total current into a surface integral of whatever goes through the surface. Now you have a surface integral on one side and a surface integral on the other side. Next thing you know, you have the differential form of Ampere's law, which is the curl of the B field is equal to mu naught J.
Oh.
And J is the current per unit volume. Okay? It turns out that law is actually wrong. It's actually wrong. And Maxwell had to correct it before including it in his equations. Now, let me give you an example of why it's wrong. Okay? So let's say we have a circuit and a capacitor. Okay? This is a very cool example.
Let's hear it.
So a circuit and a capacitor. If you draw an Amperian loop around one of the wires, you will get a magnetic field, right? Because there are charges moving in that wire.
Of course.
And that wire is actually crossing through the surface that the loop is drawing out. So there's a current, okay? There's a current moving through this circuit. And there's also, of course, there's a battery. Okay, there's a battery to create some
that's how the charge is
voltage
moving,
right?
of course.
That's how the charges are moving. Now, for reference, here's the diagram. Okay, so what happens is that if you draw your Amperian loop in the middle of the capacitor, what do you get? Well, there's no charge moving through it's a capacitor. So what happens is that if you check the current in between the capacitor, you get no current. If you check the current on the wire, you get some current. So where the discontinuity is kind of the relationship between the electric field and the current. It's kind of, how does the electric field affect the B field? Because obviously there's a B field, but you can't see it using Ampere's law. So the actual, where it comes from, you do a little bit of math, you do a little bit of physics with the knowledge that you already know. You actually find that the change in electric field is actually the correction term. So that's how, the change in electric field over time. And so the actual correction is that you have the curl of the B field is equal to, some constant times the charge or current density. And then what you do is you actually have to add the change in electric field over time to that, because in this capacitor example, you have a part in your circuit that has no actual current, but there is an electric field that changes over time. So that actually accounts for the B field. And what we learned here is that a changing electric field induces a magnetic field.
So each one of these laws basically has like a good meaning, like a good reasoning behind it, and like a good motivation for each separate one even being true.
Yeah.
Right. So wait, this was the last one? Third one.
Third one.
One more, right?
I mean, I can just go quickly through the last one.
Last one would just be what?
This is Faraday's law. The curl of the electric field is equal to minus the change in B field over time. It's pretty much exactly what I just said, except reverse,
I can understand that.
Except reverse the roles.
Yeah. Because this is the curl of the energy, and I mean the electric, and the other one was the curl of the magnetic. Yeah, exactly. Okay,
each Maxwell equation is a divergence or a curl, and you have an electric field and a B field. So you check the divergence of each and the curl of each, and you see what each one of them is equal to.
Well, that's Maxwell's equations for you. I mean, that was pretty advanced though.
There are actual issues.
Okay.
One of the issues is that the equations aren't symmetric, which means that you have the reason why is because in electrostatics you have this point charge. You can have a positive or a negative separate from each other.
Valid. Yeah.
But in magnetostatics, there's no such thing as a magnetic monopole. Mm-hmm. That's something they've been looking for a very long time. Yeah. And so this magnetic monopole is actually what causes, or lack thereof, is what causes this asymmetry in Maxwell's equations. Technically, in Maxwell's equations, we should see that because we have Gauss's law, which we see the divergence of the electric field is equal to the charge distribution. But when you take the divergence of the B field, you get 0. But if there were magnetic monopoles, it would actually be equal to the magnetic charge, like the magnetic distribution.
No, that makes sense. I understand what you're saying.
No, you would get that.
I understand what you're saying.
You get
because of the lack of monopoles, like the Gauss's law for magnetism is just 0.
Yeah.
And that actually does make sense. Yeah. That actually does make sense.
And also the correction term that was added to Faraday's law. If there was a magnetic monopole, there would be also a correction term to Ampere's law.
Mm-hmm. Basically, again, just for a quick recap for what the satisfaction would be if the monopole did exist. So we had Gauss's law that equaled a certain value, or at least the divergence equaled a certain value, and it was a positive value, right? Or at least it was the density of the charge. And in the magnetos case, because of that totally makes sense now, because of the lack of the individual magnets, I guess individual magnets,
like monopole,
like, you know what I mean, like the individual poles Because those don't exist, it's simply zero.
Because what you
And
study,
you can't get a density.
what you study in magnetostatics
I get that.
is the steady flow of electrons. You can't take apart like a section of a circuit and like study that, because the electrons leave
Won't
and it's
flow.
like there's no more electrons.
Valid.
You need to study like an actual circuit that keeps going in a steady flow, and that's why they call it magnetostatics. It's not that it's static, the charges are moving, but the flow is steady. So it's the static in that
Because
way.
there is electrostatics and electrodynamics, which are actually different things, because they do talk
Yeah.
about static charges and dynamic charges, where the charges itself are also flowing and stuff like that, which does introduce a level of complexity. But that was basically the Maxwell's equation that I found super interesting.
Yeah, I tried. I mean,
To anyone who is not in university, that probably did
I
not
don't
make
know
any
if that
sense
made
to you.
sense.
Probably none
I
whatsoever.
really don't.
Because the divergence, the curl, they're all terms that are not even right.
Also, this is coming from somebody who literally took 1 semester of electromagnetism.
Valid.
So
Also,
the way that
by
I
the way,
explained it
yeah.
could have been bad,
No,
just
but
in general.
maybe in the future we're definitely gonna have better explanations. But like the divergence and the curl thing, like I think that's the biggest mathematical boundary. Because
Yeah.
again, the importance of any of these relationships, any of these equations is the relationships, right? It's not really the equation. That's why I was trying to say don't just like regurgitate the equation, because there's no point of that.
Yeah.
The whole purpose of these equations is to understand the relationship between these variables, or between these variables. And now we have it got with that. That's pretty cool.
So anyway, the last thing I wanted to say about Maxwell is that he actually produced the first color image ever, which is pretty
that's
interesting.
cool.
But I mean, I don't really feel like going into that right now.
I think that's cool.
So
one thing I want to end off with Boltzmann, just continuing on his craziness with statistics, because like I'm in statistics, guys. Like I love Boltzmann and what he's done for physics, because again, like it's huge. And again, with just the Boltzmann distribution, something that he continued on for a long time, that's literally the foundations of statistical mechanics today, is basically again just the relationship between a body's energy, or the average energy that the system will experience, and the velocity of its particles. Basically the speed distribution, the Boltzmann speed distribution, usually what it's called, of any system. And and this is literally, it's simply a relationship basically between the properties of the system and again the speed. And more mathematically, more rather than the speed, it's actually a probability statement, because again, this whole thing is started with statistics. So to be more accurate, if I want to take it that step further, which I do, it is more of a probability statement stating the probability that the system will be in a certain state given certain parameters, right? And this is literally applicable for any realistic system, right? I mean, no perfect system is ideal, and this takes that into consideration too. So the whole inclusion of the distribution, he basically invented a field of physics, is what he did, right? Because that's you can think about it like that. And I think it's really cool how he used a lot of Maxwell's laws to kind of help assist in those formulae, because the Maxwell-Boltzmann distribution was completely Boltzmann. It's just Maxwell's laws that allowed him to prove that his equations worked, right? Because a lot of it was for electromagnetism as well, which is then he used with Maxwell's equations. So that's basically Boltzmann.
all right.
I don't think I'm missing anything else, anything big at least.
Sick.
Yeah, that's basically Boltzmann.
Well, thank you everybody.
Anything about Maxwell you want to add?
No, I'm good, thanks.
I think that Maxwell equation thing definitely dragged you, definitely tired you out. But that's James Clerk Maxwell and Ludwig Clerk. James Clerk Maxwell and Ludwig Boltzmann.
All right. Thank you for listening to this episode. If you enjoyed, make sure to follow, like, comment everywhere, and also come and subscribe on YouTube.
Come follow our Instagram page at math.physics.podcast, where we always keep our viewers updated with everything that's going on. This very week, we had Tejas Weenie, our very first giveaway winner. receive her shirt. I know I mentioned that she would receive it like a week or two ago.
She got it.
There were a few complications, but now she's got it. So that's finally there. And she's really happy. I'm really happy that she's happy. So that's really cool. More giveaways to come. Stay tuned for a really cool giveaway that's about to be coming.
Oh, yeah.
So get ready to type those comments because hint, hint. Hint, hint.
So this officially has been episode number 80 of the Math and Physics podcast. I am your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.
See ya.